Good afternoon. Time is relative. I want you to take a moment to think about what real time means to you. Really, take a moment. I'm going to just, like I was just introduced, I'm Noah Pritikin. I'm the lead SRE at Kount for the AI team. And it's been a pleasure to be here and talk to you guys about what we've got going on at Kount. So do you have your definition yet? See some heads nodding. This is good. OK. Well, without really knowing what you thought of, I think I know that your answer is right, because it's a relative term. We're all right with what we think real time means. But this talk is not about defining language. We're here to talk about the real-time architecture that we built at Kount for executing our machine learning models in real time. So I'm going to use a human learning technique and talk about two things. Machine learning applications. And we're going to divide these two things into, or divide machine learning applications into two pieces. And I'm not a data scientist. I'm an SRE. This is an operations role. But I know that this pie chart is perfectly to scale. OK? All right, so non-real time and real time. So some example non-real time machine learning applications. Agriculture applications we apply machine learning to, weather forecasting, marketing, things of that nature. So real time. Detecting credit card fraud. This is what Kount does. This is our main product we sell. For the purposes of my presentation, I'm going to define real time as less than 100 milliseconds. But again, we're all right, however we decided to define real time. So here's what we're going to talk a little bit about today. What is Kount? I'll give you a brief, very brief intro on Kount. We're going to talk about the data pipeline context, where this talk fits into a bigger picture. I'm going to kind of deep dive into the actual architecture that we built at Kount, that we've had in production now for about a year and a half. And then we'll talk about how we've applied some statistics to making sure that the architecture is performing as we expect. And then hopefully we'll have some time for Q&A. OK, so what is Kount? Kount provides a fully featured software as a service solution for fighting fraud and boosting revenue for about over 6,500 clients or merchants. So typically, this is an online merchant that sells product, and the merchant will send us their transactional data so that we can analyze it for fraud and give them responses back. But most companies think that a fraud solution's purpose in life is to just decrease fraud. Well, that's just really half of the story. The other half of the story is to increase sales. Well, at Kount, we take both of those things very seriously. And so we've created a solution that not only decreases fraud, but will boost revenue. Because if we just focused on fraud, we would actually be eliminating good transactions and thus maybe turning away good customers from those merchants. And that's not good for merchants. Those merchants want customers to buy their product. If we start turning away good people and good credit cards, that's not going to be a good thing for them. OK, so let's talk context. So I'm going to walk through a slide here. So here you are. You're going to go to your favorite online retailer. You're going to buy your favorite product from them and use your favorite credit card. And that transaction, you put all of your information in the shopping cart. You click checkout or purchase. That transaction will be sent to Kount and analyzed in real time for fraud. And that score or prediction on fraud is going to be sent back to the merchant for disposition of how they believe needs to be disposed of. So in other words, we'll give the merchant the data, and they'll make a decision if it's something they want to approve, decline, or hold for review. After that transaction gets back to the merchant, that gets stored off in Kount's data lake, which, yeah, that really doesn't look much like a lake. Ah, there we go. OK. So now we've got our data lake. We're collecting historical transactions. And Apache Spark and HDFS are used here to pull that information over offline to generate and train our machine learning models. So in a previous talk, Josh Johnston talked a little bit about the improvements that we've made at Kount around our data pipeline and the training processes and tools that we have in place to help support making sure that we have a very rigorous scientific method around tracking and the traceability of those models and how they get produced. So if you didn't get a chance to listen to his talk, please go back to the recording. It's going to be, it was a really great talk and give you some good context to the first half of what I'm going to be talking about. So again, I'm not a data scientist, OK? There's some magic data science fairy dust that occurs after in the Spark land that will generate us a model. And in this case, we're talking about an MLeap pipeline. This zip file is a really important artifact that gets stored with MLflow. And in the processes that Josh talked about in his talk, we use MLflow as a traceability to make sure that we have all of the different artifacts associated with the different experiments that we run. That particular model, once it's deemed to be good enough to put into production, he'll hand over from a roles and responsibilities perspective. He'll hand over to the operations side of Kount, which is me at the moment for the AI team. I'll take this particular MLeap pipeline and put that onto our API servers where MLeap is hosted. And our machine learning execution platform will utilize the cluster of MLeap servers to generate those predictions and send those predictions back to the merchant. And all of this happens in under 250 milliseconds. In the case of the real-time machine learning execution platform, it's actually more like 10 milliseconds. But end-to-end, our SLAs with our merchants are usually approximately 250 milliseconds. OK, so here's the context part of this. The part that it just got grayed out is what Josh talked about. The part that I'm going to focus on is what's still there. And this is about the machine learning execution platform and the architecture behind that and what we did. So let's briefly go into some of the history. So earlier on, we released Boost technology in October of 2017. And we were leveraging the Kount data lake that I visualized for you in the last slide to, we brought that forward to have the Python processes that were there to train models. We were doing that all and hosting those models in one single solution. And what I mean by that is a single virtual machine or a single server was hosting the entire stack for serving up that model. We had a Python 3 process pool that loaded a pickled model into memory upon startup. That model then got evaluated with, as we had a stream of real-time transactions come through that infrastructure, and we had predictions that were generated and sent back to the merchants. That was all fine, except we had a lot of problems with that. So we lacked a lot of portability. We lacked the ability to change like the version of joblib and scikit-learn because it was tied back to and frozen with how that model was trained back in the pre-production part of this process. So when Josh and the other data scientists at Kount trained a model, the version of scikit-lib, or excuse me, scikit and joblib, and the other Python 3 modules that we had in that environment had to kind of be carried with that particular model into production. And so making changes was very fragile. We had to make sure, and we're very careful with making changes to our model. And it was also challenging to scale because we had all of these things, these services, that were there necessary to host a model and provide predictions, all in one kind of monolithic server. It really lacked the ability to kind of scale everything together, didn't really make it easy. And then we wanted to host multiple models. So what happens when we want to change a model? Well, we have one running, and then we want to have another one that we want to migrate our production traffic to. Well, we can't really do that in this architecture. And then also, we had limited model governance. So how do we know what's running in our infrastructure? Well, when Josh asked me, I would go look on the file system, and I'd say, well, this file name is what we've got running in production right now. That really doesn't cut it. We can't really tie that back to the previous training and the artifacts that were built and the experimentation that was done. We can't really tie that stuff back to where we were with the why we have a particular model, why we don't have a particular set of models associated with all the experiments that were done in training. So fast forward a little bit. In January of 2018, we built our in-house on-prem Apache Spark cluster, and we began iterating on the model for Boost. This includes things like additional feature engineering. We were looking at adding features, removing features. We were tuning the model hyperparameters, doing grid searches. This was all made possible based on the fact that we could do a lot more distributed processing with a tool like Apache Spark. It was pretty awesome. But then we had a problem. Apache Spark and the ML-generated models depend on a Spark context to run. So what do? We have this model, this great model that was running really well and is very accurate in detecting fraud. But we can't serve our stream of real-time predictions back to merchants with a Spark context in that function. So this was our first iteration for our next improvement. And this is where MLeap comes in. MLeap really allowed us to take this next step in our continuous improvement journey and look at what this next architecture is going to be. OK, so here's the architecture diagram. And I'm sorry it's kind of small, but I'll give you a moment to just look at that. So I'm going to highlight a few things here. So if you remember the diagram that we saw before, where I gave you some of the context, this is basically the same thing. We've got the transaction coming in at the top on the left-hand side, and it comes into the process pool and goes through a feature extraction process kind of cluster. So where we do data munging, all the feature engineering happens in that cluster. And then we have a load balancer that is responsible, that sits next to all the feature engineering that interfaces with all of the MLeap instances that host MLeap in a highly available, reliable environment and cluster of their own. Our data lake. Yeah, we need that back. OK, so one of the big advantages of this particular architecture is that the feature extraction processor instances in that top kind of horizontal cluster there is separated from MLeap. So now we have the actual execution where we do the transaction, the predictions of those streams of transactions. Those two things are now completely separated physically by the fact that they're on different servers. This allows us to scale things differently and appropriately depending on what those particular requirements of that particular service demands. In addition, we wanted to be able to host multiple models in this architecture. We needed the ability to change models. So when we have, after about 9 months or so, we realized that our machine learning model for Boost started to drift a little bit in terms of accuracy. Well, we're looking at retraining and making sure that we get the latest and most accurate model out there for our merchants to use. But how do we do that without having any planned downtime? We are a 4-9 shop with no planned downtime all year long. So that's like about 30 minutes of unplanned downtime a year. So the way that we enable this behavior is by using MLeap and multiple instances of MLeap. And the latest version of MLeap, I believe, is .13 at the moment. It supports multiple models natively, which is awesome. Our current architecture uses, I think, .11, which .13 is where they introduced that feature. But in .11, Kount submitted a pull request and got that approved into the MLeap project for being able to host and parameterize running MLeap instances on specific TCP ports. So if you think about, I've got one server, I want to run 4 instances of MLeap. Well, unless you do it on different IP addresses or different ports, those are kind of your two flavors of being able to run multiple services on the same box, in the same network stack. So we chose hosting on multiple ports. And in fact, the pull request was specifically talking about having MLeap run on either an IP address or a port of our choosing, depending on whatever the environment told that instance to go run on. So in our case, we have MLeap running on, in the picture, it looks like it's showing port 10,000, 10,001, and then 10,002, 10,003. So we've got 4 instances running in production. At any one time, multiple instances could be running different models. And that's great. This allows us to move traffic from one particular MLeap model to another without impacting the real-time nature of our data processing. Model governance is a big deal for us. We have built this in from the beginning, at least with this architecture. The little box there in the very middle I'm going to go into, I believe, on the next slide or the slide after that. But model governance is very important, where we want to make sure we understand where that model came from, what model is running in what environment. So I talked briefly about the load balancer. I want to go into a little bit more detail here, because I think it's very interesting to talk about how we've architected this piece. Because the load balancer is sitting on the same server as the feature extraction processor instances, the feature extraction processors don't really have to care about that particular function. Meaning, the load balancer is there serving up a particular pathway to MLeap on localhost. So we can scale out the number of feature extraction processor instances if the man needs it. And the logic, application logic of that particular function doesn't have to change. It can always just send the traffic for predictions to localhost on whatever port that model happens to be running on. So the load balancer also has a very important job of making sure that MLeap instance is alive and ready. So from a high availability standpoint, what we do in training of this model back in Spark is when we create and export that pipeline into an MLeap pipeline, that zip file that is the artifact from that process we insert a test frame into that zip file from we just grab a transaction from our test data and then insert that into the zip file as a separate file inside there. And we have a common name for that, so that when that model gets loaded up into MLeap and is sitting there on disk on the MLeap servers, the load balancer will go in and send a particular request to pull out that particular test frame and then run that through the MLeap instance to see if we do some validation around, do we have the right features and the right, for that MLeap instance to serve predictions correctly. So we kind of utilize the fact that, oh, it's just a zip file. We can put some other really cool metadata in there as well to take advantage of enabling that high availability. And I just talked a little about backend health checks, makes predictions on that test transaction. So those MLeap API servers, we have some GC optimized Java 8 configuration that they run behind. And then also metrics to make sure that Java is healthy, garbage collection is doing what it's supposed to do, nothing's out of whack, because when Java gets out of whack, it really goes out of whack. OK, so let's talk about dark production infrastructure. Now let's really talk about dark production infrastructure. So what do I mean by dark production infrastructure? Why do we need this? What happens when we want to change a model? Well, where do we put it? Do we go straight into production when we want to change it? No, we don't. We go into a dark production infrastructure. And what that means is we have a entirely separate parallel infrastructure that's in our production environment that's not customer facing. The reason we want to do that and require this kind of behavior is that we need the ability to run a model against production data, because of the diversity of that data coming through our stream of production transactions cannot be replicated in a non-production environment. We cannot replicate the diversity and the uniqueness of the data that we get from our merchants in a QA or integration or some other non-production environment, within Kount. So we need the data from production to flow through that model, to look at its accuracy, and the data scientists will look at validating to make sure that that model is performing as they expect against actual production data, but not make this customer facing. There are no real-time requirements with our dark production infrastructure. There's no customer impact because there's no customers using it. It's just an internal tool for us to be able to use production data with the model that we generate and are wanting to use or replace with whatever's currently in our kind of customer-facing infrastructure. So we achieve this through some parallelization, using some type of message bus, whether that's Kafka or Kinesis or ZeroMQ, or you pick your flavor of message bus. And we also optimize the cost. We don't need to have the same scale that our customer-facing infrastructure has. Maybe we'll just process 1/3 of the transactions. That's perfectly fine. It will take us 3 times as long to get the same volume, but that's OK. We can sit on a model that we think is probably pretty good in the dark production infrastructure for a week or 2 or 3 and get the same volume and analysis that we would do kind of offline to validate that that particular model is performing as expected. To achieve this, we only log those raw predictions from MLeap for later analysis. None of those predictions actually get sent back to the customers again. This is not customer-facing. What this does achieve for us, though, is it really enables our ability to, it enables our ability to do model governance and validation. So let's talk about some of the tooling that enables our model governance. So that's this little box in the very middle. Model governance data store is important to centrally track the entire state of a model end-to-end in its entire lifecycle. So the moment we put it into the dark production infrastructure, it's tracked in that particular data store. And as it moves through its lifecycle until it's completely retired, we track all of those changes of state so that that particular deployed environment and where that infrastructure sits, we know what's running there. I don't have to go look on the file system and say, I think it's this file name here, and I'm pretty sure that's the one, if I can remember correctly. We don't have to do that anymore. I'll just go there and say, yep, this is what's in production, because there is no other possible way and mechanism that we built that would allow any other model to run other than what's captured in that data store. So let's go through a quick example of kind of what model governance might look like. So data scientists will use Spark and HDFS to train a model and verify its quality using test data. Once they feel like that particular model is probably ready for production, we're going to add it to the model governance data store. And we're going to deploy that model to the dark production infrastructure. So we let it sit there for some period of time, like I said, depending on how much volume we need. And if it's not looking good, we'll go back and maybe look at the data again, and maybe do some additional feature engineering or whatever other data science-y magic fairy dust that needs to occur to make sure that that particular model is up to snuff. If it does look good, we're going to deploy that particular and promote that model to our production, client-facing, the real thing infrastructure that is hosting that particular model. So if we've replaced a model, we want to migrate our traffic from the MLeap instances that is hosting the currently running model to the one we just put out there in a new set of MLeap instances. So this is the blue-green deployment approach, if you've heard that term, or the ability to have no downtime. It's very important to be able to have that high availability. So we'll put a model into the instances of MLeap where we've got kind of two models running simultaneously. One of them is generating predictions for all the traffic, and we'll migrate and move, kind of swing over the production traffic from the old one to the new one in real time while we're doing stream processing. So once all of the traffic, all that production traffic is now moved over to the new model, we will unload that particular model and retire it from service and capture all of that state change in our model governance data store. So again, it's about centrally tracking the state of machine learning models end to end for the entire lifecycle. OK, statistical metrics and monitoring. So with a real-time architecture, performance from my standpoint, from an operations standpoint, is not about the data science performance. So we're not talking about total operating characteristic curves. We're not talking about precision recall curves. We're not talking about the different curves that you might look at from a data science perspective to see if your model is doing what it's supposed to do or what you'd like it to do. If we have a real-time architecture, like we built at Kount, we're going to need real-time metrics in order to measure the systemic performance. So we need some tools to be able to help us do that. Traditionally, we might be looking at averages, maybe even percentiles, and those are great. This looks really fast, right? 6 milliseconds? That's great. It's a great average. What happens when we say, we're going to, hey, that average improved 20%? What improved 20%? It's really hard to know how this needle moves back and forth without knowing kind of what's going on underneath. So averages don't really cut it by themselves. But distributions, those are the key to this madness. So when we have distributions, we have, this is a histogram of all the transactions in a given time period and how much time, what the latency is for each of those transactions. And they're bucketed by latency, by the time that they took. So in this particular case, this is a plot of the distribution for that average. So when I said that that average may have improved by 20%, maybe that means that the huge chunk of transactions that are on the left side of this diagram got a lot faster. But we still have all of those on the right side that are really, really, really slow. That, if you can't really see those numbers, those go up to like 53 milliseconds. That tail is long. So distributions really provide a critical visibility in monitoring low latency systems. So let's talk about our production architecture and how it's been performing for us. So here's our first iteration before our continuous improvement effort. Boost without MLeap. This is what was going on before. So we had an average, and this is actual real production data over a period of, I think, 24 hours. Can't remember exactly what time period, but this was before we started using MLeap. So we had an average of about 19 milliseconds. Our 95th percentile was 24 milliseconds, et cetera, et cetera. And you can see there that our distribution is right below it. And I've kind of marked on the diagram that line furthest to the left there you'll see is the average at 19 milliseconds. And then the next line right after that is the 95th percentile. And then the one after that's the 99th. But you can see the tail is really long. It goes way out to the right. If somehow we can bring in that tail, make that tail a lot shorter, our average was going to go up our average is going to get better, but it's going to go down quite a bit. So that's what we've got to start looking at, is using tools like this to really help us hone in on what is going wrong with those transactions that are really far out there on the right. Why are they dragging our average bad? And here's Boost with MLeap. So we cut our average down from 19 milliseconds down to 7. But again, these are averages. Like, who cares about averages, right? I mean, they're great, but distributions are better. Our 95th percentile went from 24 milliseconds down to 9. Our 99th percentiles went from 37 down to 16. You can see how the two distributions are kind of staggered. That's on purpose. I tried to line up the timing buckets based on how they're actually shown there for you. You can see that our 99th percentile with MLeap is even faster than our average without MLeap. I mean, this is crazy better. This is a 56% improvement just with our 99th percentile. I mean, that's awesome. That means we did something right. And not only did we do it right, we did it in a reliable way. We have model governance. We have high availability so that we're up a lot. We're pushing on 4 nines. So here's some things I want you to consider about your real-time architecture. Consider using MLeap if you can. It's a great tool. It's an open source project that really enabled Kount to take the next step in our journey with machine learning and using distributed tools like Spark to be able to generate models, but then actually use those models in production in a real-time way. Model governance. Our model governance has been a big part of the journey with this architecture. The dark production infrastructure is a very interesting function for you to think about, assisting with model validation using real live data, but that's not customer facing. And then, of course, latency metrics. So again, emphasizing the use of distributions. Don't just look at averages, or maybe even percentiles are great, but distributions are very, very, very helpful. Here's some further reading. I did a blog post, or I guess this is more of a case study with the Combust ML folks that created MLeap. They were gracious enough to post this on Medium for me. It kind of goes into more detail about this particular architecture. So check that out if you're interested to learn a little more. And then here's some of MLeap's documentation. Thank you so much. Appreciate it.
If we have questions for Noah, we have time for a couple questions.
So I got two.
Yeah, which one do you want? The previous slide? Sure.
So I have two questions.
Yeah.
One, what do you do if you don't meet that latency and it's past that 250? Do you have some sort of fallback around that? Or if an error occurs in producing the result from that? That's one. And sort of related to the dark production side, when you switch out the model, or there's a new model that comes into play and the features are different, how does that kind of work within that framework?
Sure. OK, so the first question was about what happens when we're past our SLA, basically, right? OK. So when we are past our SLA, we give the merchant a default kind of middle of the line score. So if let's just, for example, for sake of an answer, if our predictions go from a scale from 0 to 100, maybe we'll give them a 50, because we don't know if it's good, we don't know if it's bad, but it's going to be something. So we give them a 50. The other question you had was around the dark production infrastructure and kind of what we do when the features change. Yeah. So when we have model changes where we do either feature reduction or feature, when we expand features, increase features, the application code that goes along with the model will have to change with the model. So when they get deployed, they'll be deployed together. Yeah.
Thank you.
Sure.
Hey, so I was wondering what your thoughts were on the difference between dark production environment and a staging environment. Is it fair to say maybe dark production is a subset of architecture just for some ML use case, and maybe staging is like your whole platform, or are they more or less synonymous in what they're trying to do? Or?
Let me make sure I got your question right. So you're wondering about the specifics about the dark production infrastructure and kind of what it's made up of?
Like, would you say it's the same thing as what someone's staging environment would try to do, or are they like different, or are they trying to do different things, or?
They're doing exactly the same thing,
Sure.
Maybe just with a different model.
Okay, sure.
Yeah, does that make sense?
Yeah, sure, that's fine.
Okay, yeah, if you have additional questions, let me know.
Do you use some kind of an acceleration for boost and see if things can be even smaller? I mean, the numbers that you have.
I'm sorry, can you speak up?
The accelerations?
Oh, accelerations?
Yeah.
No, we don't. We don't use any hardware accelerations, or no.
You've been talking about training whole pipelines and deploying, exporting them as MLeap pipelines. But then in the production side, you've got one set of servers doing feature extraction and one set of servers doing prediction. Is that those two things are both part? How does that work if a pipeline contains both feature extraction and prediction?
So that's one of the things that we broke apart as part of this architecture, so that they could scale kind of independently. And I didn't quite understand the question.
So when you when you train, because
Oh,
in the training part
sure.
you're talking about pipelines, which to
Yeah.
me sounds like the artifact you're delivering contains the transformations and the prediction model.
So we don't actually do any transformations within Spark.
Okay.
Yeah, so the transformations occur within the application code
Right.
and also within the code that's used for training, but we don't actually build in any native like Spark transformations
Right.
for our models.
So the pipeline that you deliver after training, that only contains the model itself and not any of the feature extractors.
Correct. Yeah, it's just the model.
I think we're a little over time here, so we can continue questions off the mics up front. And I just really want to thank Noah for coming in to speak today. Thank you so much, Noah.